In lesson 1.15 inverse functions, the objective in this lesson is to determine the domain and range of an inverse of a function. You will also learn to determine if a function is one-to-one, which is directly correlating whether a function has an inverse or not. So let's begin with what an inverse function is. Now, an inverse function simply switches the independent and dependent variable. So an inverse function simply is going to switch the x with the y's, and as a result is going to give me a function that does the opposite operation of the initial function. So for example, here we have a function that multiplies again our input value with 2. By switching the x and the y and solving the equation for y, I now have a function that divides our input value of 2. So one function multiplies all our numbers of x by 2, and the other function does the opposite and divides all of those numbers by 2. And that's what an inverse function does. And because we're switching the independent and dependent variables to get an opposite function, an inverse function, opposite function, then this affects the domain and range by switching those two things as illustrated in this diagram. The domain of a function is the range of its inverse, and the range of the function is the domain of its inverse. So here, if this is the domain for the function f, and this is the range for the function again f, then the range becomes the domain for the inverse, and the domain becomes the range for the inverse. It just simply switches. Therefore, if we look at our first example, example number 1 in our notes, before we go to that, so the notation that we use, as you see right here, for inverse is this notation right here. We have f to the negative 1. So the notation for an inverse is to have our function f putting negative 1 as an exponent, again in terms of x. And the way that this is read as f inverse of x. That's how we read this notation. So let's look at some examples on how we're going to find the domain and the range to an inverse. So let's look at example number 1. On example number 1, we see that this right here is going to represent a function f. So let's put this in a tabular view. So we have our domain and our range for our functions. We have negative 1, negative 1. We have 7, 4, 3, 0, and negative 5, negative 1. So this is the domain, again, of our function f, and this is the range of our function f. So to identify the domain for the inverse, it's simply going to be the opposites to this. So if this is the domain of f and this is the range of f, then this is going to become the domain of our inverse. We just simply switch the x and the y. So the domain to the inverse is going to be the set of negative 1, positive 4, and 0. Well, negative 1 also, but that number is already in the list. So this is going to be the domain for f inverse. And the range for f inverse is going to be the domain of the function. So our range is negative 1, positive 7, positive 3, and negative 5. Let's look at another example. So here we have the function where we're mapping 1 to 9, 2 to 7, 3 to 6, and 4 to 8. So again, since this is the domain for f of x, and this is the range for f of x, the domain for the inverse of this function will simply be the range. So the domain would be 9, 8, 7, and 6, or 6, 7, 8, 9. And then we switch the domain for the range for the inverse. So the range of the inverse would be the numbers 1, 2, 3, and 4. So all it does is simply switch. Now, if we have a graph instead of a mapping or an ordered pair, again, the way that we find the domain and range for our inverse is by simply now looking again by switching the domain and range of the function. So the domain for our inverse. Well, normally we get the domain of a function by looking again horizontally from left to right. And we would see that this function doesn't go any further than 1 and doesn't go any further than 5. So that would be the domain for f. Our domain would be from 1 to 5. But the domain of the inverse is the range of this function. So to get our domain here for the inverse, we are going to look at the range of this graph. Because again, this is for f of x. So the lowest that this graph reaches is -3, and the highest that the graph reaches is +5. So our domain here is going to be all of the x values greater than -3 but less than +5. And it's going to be a closed interval because we have closed circles on top. Now the range of the inverse is the domain of the function. So looking at the domain for this, again, we're going from +1 to +5. So our domain would be from 1 to 5. And again, since those endpoints are closed, it would be a closed interval. So for this, another example, let's look at this example, the square root one. Let's figure out the domain and range for the inverse of this square root function. So this graph right here, again, this is f of x. So this is f of x. And I want to find the domain for the inverse of this graph. So I want to find the domain for the inverse to this graph right here, okay? Well, since the domain and range switches for the inverse, the way I find the domain is by looking at the range. And this graph exists again above the y value of -4. It has no upper boundary. It's going to continue moving up, up, and up. So there is no upper boundary. It does not stop right here at this value or nor at 0. It continues moving up. So our domain here, our range, which is the domain of our inverse, is going to be all of the values of all of the values of x greater than or equal to -4. So as an interval, that will go from -4 to infinity. Now, the range of the inverse is the domain of this function here. So here, the domain of this thing exists to the right of -3, and again, there is no boundary to the far right. So -3 is the farthest left that it goes, but there's no boundary here on the right. It's going to keep on going towards positive infinity. So our range are all the y values from -3 to infinity. So that's our range. Again, it just simply switches. If you find the domain of this thing and the range, that's going to switch, and that the range becomes the domain and the domain becomes the range. So just simply they simply get switched again. Now, because we're switching again the x and the y value, a function again we can identify if a function has an inverse by looking again at a graph. A function f has an inverse if and only if no horizontal line intersects the graph of f at more than one point. What this simply means is that if no horizontal line intersects the graph of the function at more than one point, then the y values is going to match exactly with no more than one x value. We call this a one-to-one function. This is referred to as a one-to-one function. And if a function is one-to-one, that means that a function has an inverse. So a one-to-one function relationship and the inverse are going to be functions, and vice versa. A function has an inverse if and only if the function is one-to-one. So this terminology simply means that we have an inverse. So we have a one-to-one function, then we have an inverse, and vice versa. If we have an inverse, then we have a one-to-one function. They mean the exact same thing. So, and the way we determine it, we have again this one-to-one function is by using again a horizontal line test for graphs to give a visual idea if a function is going to have an inverse. So for example, this right here is a function. This is y is equal to the square root, or let me write f of x. F of x is equal to the square root because it's quadratic, and since it's shifted 1, 2, 3, 4, 5 units down, minus 5. Now, this function here, if I use the horizontal line test and draw a horizontal line, I see that my horizontal line intersects the function at more than one location, at multiple locations. Because of this, this is not one-to-one. Which means that every x value might have only one y value, but not every y value has only one x value. So, for example, right here, at 2 and at 3, let me make it a little bit bigger. So at -2, +2, -3, and +3, -4 has a y value of -1, +2 has a y value of -1, negative and +3 have a y value of +4. So this is a function because all of these x values have only one y value. But this is not one-to-one because going in the opposite direction, this number has two x values, and this y value has two x values. So this is why this is not referred to as a one-to-one function. And since it's not a one-to-one function, the inverse does not exist. So this graph is not going to have an inverse. Compare that to example number 6. Here, this does have an inverse, because even though it looks like this is horizontal, it is not. It's just approaching this horizontal line. So it's not really horizontal to this line right here, and any other red line that any other red horizontal line I make, it's only going to touch the function at one location. This looks horizontal at this location here, towards this portion, because I'm really zoomed out. But if I was to zoom in, I would see that the graph is gradually decreasing and decreasing, getting closer and closer to +2. But it's never actually going to touch. So as a result, this graph here is a one-to-one function. So this is a one-to-one function. And what this implies is that the inverse exists. So again, one-to-one implies that we have an inverse and vice versa. An inverse existing implies that the function is one-to-one. All right, so write your answer for this, determine if this is one-to-one, and then come back and check your answer. So this function is one-to-one. This is a one-to-one function, and therefore the inverse exists. This thing is going to have an inverse. And the last one. I know this looks kind of tricky, but here, this is not really horizontal in that location. So here, there's only one point that's touching, again, this horizontal line, which is going to be, again, at 0, -1. Only there do we actually touch the horizontal line at -1. All the other points is because we're too zoomed out to tell that this portion of the graph keeps getting closer, closer, and closer to this horizontal line, but only right here are we actually touching the horizontal line. As soon as we move any unit, a micro unit, away from that, the graph starts moving up and is not touching the graph anymore. So this does pass the horizontal line test, and therefore this is a one-to-one function, which means that the inverse of this function is going to exist. And there you have it. All right. Thank you again for watching. If you do have any questions about inverses and the horizontal line test and one-to-one, again, send me a message through Remind or an email. I appreciate you watching again, and I hope you have a great day.